Okay. Now somebody with a microphone tell me if you can see my PowerPoint.
I can see it.
Thank you. All right, so for this session, it's going to be pretty quick because we haven't really talked about that much since our exam. But this is going to focus on osmosis, active transport, and introduce metabolism a little bit. Okay, so the first thing is osmosis. You need to remember osmosis, like the solutes don't move. In strict, plain osmosis, that occurs when molecules are too fat to seep through the membrane themselves. So if you have a huge sucrose molecule, which I know you guys don't know what that looks like, but it is basically like two big circles joined together. That's not going through a membrane in the way that we're used to. So in that case, the water is going to move to dilute something. So here, see, we have, let me blow this picture up so you guys can see it better. Okay, so here we have a low concentration of solute, so we only have U, and then we have a high concentration of solute. So in a perfect world where diffusion could happen, you would just say, okay, this is going to go across that molecule, well, that membrane is going to be fine. But remember that these molecules are too big to fit through this little semi-permeable membrane. So what is going to happen is the water is going to move to dilute the higher concentration of the solute. You can also think of it as the water moves down its concentration gradient. We have a high solutes, so we have a higher concentration of water. So basically what's happening is the water is just moving down its concentration gradient. So it'll get less on this side and it'll be more on this side. So the solutes aren't moving, the water is. All right, I know, and at least for my class on the exit ticket, a lot of people were confused by this. So do you guys have any questions? You want to talk about it? Let's talk it out. Okay. All right. So I'm going to click back up here. All right. So never mind. I'm going to do this and then I'll quiz you guys. All right. So any questions on just straight up diffusion? Not diffusion. I'm so sorry. Straight up osmosis. So if you were given a problem like this where it had a tube with a semi-permeable membrane, do you guys feel like you could do it? Are you confident? All right, I'm taking this as we're all confident. All right, so now we're going to move on to tonicity. So the easiest one is isotonic. So isotonic just means that you have the same concentration inside and outside the cell. So that's our normal little animal cell. Okay, so how I remember that is isotonic, iso happy. I know you sound like a 4-year-old saying it, but it works, I promise. So an isotonic cell is normal, is happy, is not exploding or shriveling, it is just living its happy little life. So isotonic, iso happy. Okay? Now, hypertonic is when the concentration outside of the cell is higher. So say if you put cells in salt water that aren't meant to be in salt water. Whoop. Oh, is my screen frozen?
I think it is.
Cool.
Still on the same slide. Slide 2.
Okay. Just refreshing this blank now. Y'all, don't we love Wi-Fi? Okay, I'm going to refresh, so it'll kick me out for a minute, but I will be right back. I'm just going to see if that'll help, okay? Okay, guys, let's try this again. I'm so sorry. I don't know why this always happens. It works. My Wi-Fi is never worse than when I'm doing a study session. Okay. All right. Are we good now? Can you guys see this and hear me okay?
Yep.
Yeah, I can see it.
Perfect. Okay, if that happens again, y'all gotta tell me. So thank you. Because if not, I'll just be talking along and nothing will ever get addressed. All right, so I'll start over. So isotonic is this little animal cell right here. And it has the same concentration inside the cell as outside the cell. So it's happy. Now remember, solutes are still moving in and out because even though it's equilibrium, there's still movement. There still has to be movement. If solutes aren't moving in and out, then the cell is dead. No movement means it's dead. Okay? Now, hypertonic means that the concentration outside of the cell is higher than the concentration inside of the cell. So imagine if you put like a cell in salt water. Or, okay, perfect example. You go swimming, okay? And say you're in all that chlorine and bleach and water that is saltier, let's say, than your normal body. What happens if you're in the swimming pool for a long time? Oh, come on. I know you guys have been in the swimming pool. Something happens to your fingers. They start to...
Like shrivel.
Exactly. They shrivel up. So imagine that, okay? Imagine this as you're in the swimming pool. So you're in a saltier environment. Your fingers are going to shrivel. That's an analogy to what's happening here. The cell is shriveling up and dying because all of the water is going out to dilute the environment. Okay? All right, so hypotonic, that is when inside of the cell has a higher concentration than outside of the cell. So, let me see. This would be like if you try to take a saltwater fish that has been adapted to saltwater and put it in fresh water. It's not going to work for a more complicated reason, but let's just dumb it down to this, okay? It's not going to work. So if a cell has a higher concentration than the outside, okay, water is going to rush in from the outside, and that cell is going to burst when it reaches its limit. So imagine this like a basketball. And you keep pumping air in from the environment to dilute whatever's inside, and you keep pumping and pumping and pumping, and at some point that basketball is just going to explode. It can only take so much from the environment because like a basketball or a cell is that size for a reason. It's not just that it decided to be that. There's a reason why it's that size and why it has that concentration. Okay? Any questions on osmosis or tonicity? Because I know those are kind of confusing topics if you've never seen them before.
I have a question.
Mm-hmm.
So when the cell gets shriveled up or like it bursts, does it die? Like, does it become a dead cell?
Yes, it does.
Okay, thank you.
No problem, and good question. All right, any other questions? Okay, so now we're going to move on to active transport. This is very, very simple what she wants you to know. So the main thing you need to know with active transport is that it requires ATP. Now, ATP is like the cell currency. And we'll learn all about this when we start glycolysis, I believe, in next chapter. Have you guys already talked about glycolysis in lab?
Yep.
Yep. Okay. So what is the main product of the overall respiration cycle is ATP. That's the energy. So to do active transport, you have to use some energy. Okay, and you have to do that because solutes aren't moving from concentration to low concentration. They aren't moving down their gradient, they're moving up their gradient. So they are moving from low concentration to high concentration. Okay, so this allows cells to have a different concentration than their environment, which could aid in the hypotonic situations. And an example, I know she posted this on the eLearn page, the sodium potassium pump. Highly, highly recommend that you guys go and watch that. It's just a good way to visualize what's happening. So basically, the sodium potassium pump says that sodium needs to be on one side of the cell and potassium needs to be on the other side of the cell. So they're both moving against their concentration gradient to get to where they need to be. Okay? All right, so that's all I have on membrane transport, that little bit that we didn't finish before the exam. Any other questions about that before we get onto metabolism? Okay. All right, so let's jump right in with the law of thermodynamics. So there's two main laws that you need to know. The first law is that energy cannot be created or destroyed, only transferred or transformed. So this is pretty self-explanatory. So energy can't just be created out of thin air. You can't just poof, I have energy. If it worked that way, college would be so much easier. But sadly, as we all know, I can't just shut my eyes and wish real hard and have energy. Okay, so think about it like that. What do I need to do to get energy? Do I need to drink a cup of coffee with a lot of sugar? Do I need to eat a big bowl of pasta for all the carbs? XYZ, whatever. Think about it like that. Okay? All right, so second law just means that every exchange of energy increases the entropy. Now, who can tell me what entropy is?
Isn't entropy like the natural universe wanting to have disaster or messiness? If that makes sense.
Messiness. Exactly. 110% correct. So it's just the amount of disorder. So it just means that if I eat a piece of chicken, 100% of the chicken's energy is not going to go to me. Some of it's going to be lost in heat. Some of it is going to be lost in other things. It's just the amount of disorder. It's basically saying that life is not perfect. Life is messy. Okay? All right. What is the law of conservation of mass? All right, so law of conservation of mass, think about it like the sister to the first law of thermodynamics. Anybody? Come on.
Doesn't it say that mass can't be created or destroyed?
Exactly. It just means that I can't go poof, matter. If I want to make something, I have to use something that's already existed or that's already present. That's exactly right. Thank you. All right, any questions about the thermodynamics? All right, now let's do feedback inhibition. So on my exit ticket, at least, a lot of people were confused by this, and that is perfectly okay because this is kind of complicated until you think about it and really understand what it's saying. So all this is saying is it prevents waste. So say I have made a dozen cupcakes and I can only eat a dozen cupcakes. I know that I will waste more cupcakes if I make it. So the last cupcake, that 12th cupcake, is going to shut down the pathway and is going to prevent waste. Basically, it means that there's no more room to make more product. You're out of room, you're out of space. And also, the cell knows that it can't use all of it. So the end product is going to shut down the pathway. So it's like turning off a light switch. That end product is going to flip the light switch. It's going to prevent waste. Okay. Any questions about that? Because I know that's kind of confusing. Okay. All right. Now we're going to go to catabolic pathways. So what you need to do to memorize the difference between catabolic and anabolic is you need to make charts. And make a chart that has 1, 2, 3, 4, 5, 6. Make a chart that has 6 like boxes. Okay? Give yourself 1. So give like break down complex molecules. And you have to fill in the rest. So a catabolic pathway releases energy, breaks down a complex molecule, is an exergonic reaction, has a negative delta G, and is spontaneous. So guys, I cannot stress enough, the best way to test yourself on these is to make charts. Only give yourself 1. So give yourself negative delta G. And you'll have to say, okay, negative delta G, first of all, I know it's exergonic, and I know it's spontaneous. So then that means it has to release energy and it has to break down complex molecule. Oh, so that means it's a catabolic pathway. Test yourself like this. So I'm going to skip down to, never mind. All right, so the graph, remember, is a slide. Okay? All right, so the graph is a slide. So how you can remember delta G, I know in class you was talking about like the reactants minus the products. Look at the slope of the graph. And you're not going to have to calculate rise over run or anything. But if you can just look at that slope and be like, okay, it's negative, it's decreasing, then you have a negative delta G. If the slope is increasing, then you have a positive delta G. Does that make more sense? Okay, so now on to spontaneity. How I remember which ones are spontaneous and which ones are not spontaneous is imagine I'm standing at the stairs if I fall down the stairs, that is spontaneous. Once it started, it couldn't stop, and it just happened. I didn't have to put any energy into falling. It just kind of happened, and then it progressed. Now, if I want to climb stairs, I have to think about it. I have to make my muscles move. Everything is intentional. That is non-spontaneous, and that'll go with the anabolic pathways. So imagine standing like in the middle of a staircase. Are you going to fall spontaneously, or are you going to put effort and energy into climbing the rest of the way up the stairs? All right, so the catabolic pathways are going to release energy. So the main thing is that you are going to get like ATP or some other form as a product. Now this can be used to break down complex molecules. Who can tell me in the past, specifically the biomolecule chapter, what is the word that we used to when we were talking about breaking down molecules? If I wanted to take a polymer and make it into 2 monomers, what would I do?
Isn't it hydrolysis?
Good job. Yep. So an example of a catabolic pathway would be hydrolysis, because you're breaking down complex molecules. That is exactly right. Okay? Does catabolism make a little bit more sense? Okay. Now on to anabolism. So guys, everything that I said about catabolism is the exact opposite for anabolic pathways. The exact opposite. So the graph looks like a mountain. So this is me. I'm standing in the middle of the stairs, and I decide I want to climb those stairs. So I'm putting effort and I'm putting energy into that. So this is a non-spontaneous reaction. This is an intentional reaction. Because the graph looks like a mountain, the slope is positive. So the overall slope is increasing, which means it has a positive delta G. It is considered an endergonic reaction. It consumes energy. So this is where it has to take some energy to, just like climbing up the stairs. It takes energy for me to climb up the stairs. Okay, and it builds complicated molecules. So what's the word that we know from the biomolecule chapter for something that builds complicated molecules? Come on, I know y'all know it. If catabolism was hydrolysis, then anabolism is
Dehydration synthesis.
Good job. Good job. Okay. Any more questions on catabolic or anabolic or feedback? Okay. So now you guys are going to answer these questions for me. So you are given this graph. Do not judge my handwriting. I drew this on my very old laptop like last year, and she's not pretty, but it's fine. All right, so you're given this graph. First of all, what type of pathway is it? So a thing to know is when we're talking about a pathway, we're talking about catabolism versus anabolism. When we're talking about the type of reaction, we're talking about exergonic versus endergonic. So what type of pathway is this?
Catabolic.
Okay, let's look at this. So you're reactants are down here. And it kind of starts out slow, and then it shoots up, and then your end products are higher. So that would be anabolic. It's a little mountain. So you have a little guy, he's climbing up the mountain, is going slow, and then it's whoop, and then he's at the top of the mountain. He's all happy. Does that make sense? Okay. All right, so what is the type of reaction? So we've already decided that this is an anabolic pathway. So would that be exergonic or endergonic?
Be endergonic.
Great. Good job. All right, so what is the sign on delta G? Remember to look at the slope. So this
Positive.
is exactly. Good job, y'all. Thank you for engaging. It makes it a lot more interesting. All right, so would this be spontaneous or non-spontaneous?
Non-spontaneous.
Awesome. Remember, I can't spontaneously walk up the stairs. Okay, so we haven't talked about activation energy yet, which is what this hump is. So I'm not going to expect you guys to know that that's activation energy or what it means or anything like that. So imagine that that's not even on there. Let's just look from here down. Let's look at the slide, okay? So what type of pathway is this slide?
Catabolic.
Good job. What type of reaction is it?
Exergonic.
Awesome. What's the sign on delta G?
Negative.
Perfect. Spontaneous or non-spontaneous?
Spontaneous.
Good job. Y'all blew that out of the water. Awesome, awesome job. Okay, so this is as far as we got on this PowerPoint. What I will do is I will send out the PowerPoint whole in itself. I will have another study session Monday where I will pick up from this PowerPoint where we left off. And I'll either make another PowerPoint if we get through like an introduction to glycolysis, or I'll just add it on the end. But I will send out this whole PowerPoint in itself. So you guys can have that to look at. Because we will get to most of these things before my next study session, which will just be next Monday, probably at the same time. All right. Let me stop recording.